now look at the final stages of the proof of Xiphoid-Van-Kampen theorem. First, the structure of the proof. Recall that we have this collection X alpha, alpha in A with the appropriate hypothesis, and X0 belongs to the intersection in alpha in A of X alpha. It's the base point. And we had a map phi which mapped alpha in A, all the alpha in A, the free product of the fundamental groups X alpha with X0 as base point into pi 1 of X0. And the first thing we showed is that this is surjective. Okay. And we also had N contained in phi. This is the normal subgroup generated by relations that saying that if you take something in the intersection and include it in two different spaces, you get the same loop. If you take a loop in the same intersection, so we are looking at things, elements of the following form. They're I hat alpha of j alpha beta of lambda, the loop lambda. So this should say j alpha beta star of lambda times I hat beta of j beta alpha star of lambda. Okay, so I'll just call this element G for now, and I take this element inverted, second one inverted. Okay, now if I look at phi of G, okay, so this G, of course, let's call it G lambda or something like that, and lambda is a view is in pi 1 of, in fact, it's in the loop space of X alpha intersection X beta with the usual base point. Okay, so now phi of G is, this is just inclusion map and then the formal map and then the map generated by inclusion again. So this is formally into this I alpha part is formally into the alpha component, and then I further include it. So this is simply lambda times lambda inverse, which is identity, as I said. So hence N is contained in kernel of phi. Okay, and what we need is that we have, so we have, let's call it phi bar, quotient map. The quotient map is going to be from this product alpha in A of pi 1 of X alpha X0 divided by N and into pi 1 of X0. And what we want to show is that this is an isomorphism. Namely, if I took two elements in the quotient and they go to, we already know it's surjective, so if two elements go to the same element, they are the same. Okay, you could just concentrate on identity, but that doesn't help our case here, at least following the proof in Hatcher. So what we'll do is we'll instead look at factorizations. So we look at factorizations. So this is an expression of gamma, or an element, maybe I should call it G, as gamma 1 star gamma 2, etc., where gamma n is a loop contained in some alpha n. Okay, so gamma n is in the loop space of X alpha, well, I should say gamma j more generally, alpha j and X0. So these are all loops. Now these give you factorization, so that this goes to, gives element in the free group, this guy, we'll just call it F for here, in F, hence by passing to quotients F over N. Okay, and so, and also it gives you an element, of course, in the image. That's by composing, or more directly by looking at these loops in as loops in X, and they are the same thing whether you compose or not. Okay, so these are the loops. So now suppose G prime, and let's give it a name, phi of G inside pi 1 of X comma X0. So the structure of the proof is the following. Suppose we have G prime is going to be gamma 1 prime star etc. star gamma m prime. Okay. And phi of G prime is equal to phi of G. They give you the same loop. We'll show that next, that G prime is equivalent to G under the equivalence relation we defined earlier. Okay, so hence have the same image in F over N. So these are the two main claims. The first one is the one which needs work, and we are going to show that. And now we define an equivalence relation by two moves. The first move actually gives you the same space even in the free group. The second move doesn't give you the same word in free group because we are regarding a loop as belonging to a different component. It's a loop in the intersection. However, when we quotient by n, it gives you the same element. So in F over n, if I have two elements which are equivalent, their images are the same in F over n. So what we'll show is that if phi bar of if I take two elements in the left hand side here, take corresponding factorizations. If their images are equal, then the elements are equivalent, the factorizations are equivalent, hence the elements we started with are same. This is the structure of our proof. Yeah, so again, injectivity is we take two different elements, take corresponding factorizations, look at their images. If the images coincide, which they have to if the elements have the same images under phi bar, then we show the factorizations are equivalent, and so we show the elements that they started with are the same. Okay, so this was again the structure of the proof. Now let's prove the final part, which is that two factorizations are equivalent if they have the same image, which means if they are actually homotopic. Okay, so phi of G is simply the image when we regard this as a loop. So let's see why homotopic factorizations are equivalent. Okay, so again we have factorizations. Let's say gamma is going to be gamma 1 star gamma n, and these are simply loops in gamma prime is gamma 1 prime star gamma m prime. And suppose we know that the factorizations map to the same element, which means gamma is equivalent to gamma prime. That's all that we have. So suppose we know that gamma is equivalent to gamma prime, then what do we get? Okay, then we have there exists H as usual from 0 1 0 1 to the space X. So homotopy, and we will transform this in various ways. Okay, so first of all we have a homotopy. Okay, and then use Lebesgue, etc. So now we'll focus on pictures. This is closely following Hatcher's book anyway, so you can refer there if you need written descriptions. So as usual, you can break things into bricks. Okay, and let's break them into small enough bricks so each brick goes in. We will transform this a little bit. I should say blocks at this stage. I'm using the word bricks because we're going to convert the blocks into bricks in a little while. Okay, so we have blocks, and we can't, if we divide them into small enough blocks, we can't ensure that each of these is a gamma I, but we can ensure that we have something like gamma 1, gamma 2, gamma 3, etc. Okay, that is the border points of gamma i's can be some of the vertices of these blocks. They will be additional vertices. What that means is that, so this is equivalent to gamma 1 star gamma 2. Why is that? It is equal except that we have subdivided further, and remember that subdividing further is an equivalence relation, the reverse of a move we had, which was merger. And this is equivalent to gamma 1 prime. Okay, so far so good. And we have to go from below to above. We'll make a couple of changes before we go from below to above. Okay, so the first change we'll make is let me draw a fresh picture since that is kind of important. So Let's take a rectangle here. And then let's fill it up with few lines horizontally. I'm going to have far fewer bricks just for making things easier to see. So here's a crude picture, which is a division into bricks. What I've done is shifted the side so that any vertex here, for example, this vertex is trivalent. Okay, so it involves only 3 regions, not 4. Okay, so we have vertices here. And now comes a key geometric argument. Okay, this is the one worth spelling out in detail. Okay, so can ensure, this is the main idea, vertices map to x0. And I'm going to zoom into that vertex. So, okay, so we'll do it in 2 steps. First, make h constant near the vertex. This is the main idea really, and then we can do these things. So let's zoom into a vertex. It looks like this, and let's take a neighborhood of the vertex, which maybe looks like this. This is topology after all, so we don't, the shape doesn't matter, it's only the alignment. And let's look at another copy here. Okay, and suppose this vertex is this purple color and this whole region is shaded. We have a quotient which will pinch this to a point, and you get exactly the same space. And you can do it for each vertex. Right? You can do it in the neighborhood of each vertex and with disjoint neighborhoods of each vertex. So when you map this one to this one, what happens is that the and then you look at the composition. Okay, so we take little blobs around each one of them, pinch them to point. We are getting the same space with the same brick-like alignment, and have your new homotopy is a composition of the old one with this quotienting map. So your new homotopy is going to be constant near the vertex. Okay. And then after that, after you make it constant, you radially join the boundary to x0 in the intersection of the regions. So what do I mean by that? Well, I just said Lebesgue number. Our usual Lebesgue number arguments tell you that each of these regions is contained in some specific x alpha. And because all our vertices are trivalent, any vertex is contained in at most 3 regions. Okay, so let's label these 1, 2, 3, 4, 5 this way. The labeling will be important later. 6, 7, 8, 9, 10, etc. So you wrap around, this labeling will be important. But for now, you notice that there are just regions which you can call x alpha 1, x alpha 2, x alpha 6, for example. And this this vertex is contained in x alpha 1, x alpha 6, x alpha 7. Okay, which may be 1, 2, or 3 different regions. It doesn't matter. But in how many other regions there? In the intersection of that, we have a path. So in the region, so we have this region. So the boundary is a constant. So this is constant in x alpha, whatever it is, 1 intersection x alpha, 2 so let's call it x alpha intersection x beta intersection x gamma, where these are the sets containing these. And this point is x0. There is a path, and we'll take the radial path from x0 to the given ones. And when you have this kind of radial path, we are we can replace the interior by these. Okay, so radially join and replace the interiors. What we have done is we have achieved the main thing, that is we can ensure that vertices map to x0, the given point x0. Okay, so we are there, and yeah. Okay, so this is now the key geometric argument. Now we can finish the argument by saying, so proof is just transform from factorizations by shifting across bricks. Okay, so let me sketch a few details. The key point here is that if I take any path which goes, let's say initially we'll start with the path which is the very base. Okay, which is the very base. Now after a while I might have a path, I cross 1 and 2, which is like this, 1, 2, and then this way and this way. Now given such a path, we get an associated factorization, namely every time it crosses a vertex, I split it into the path before and the path after. Okay, this is not enough, we have to make a further choice, because this segment here, for example, is clearly contained in both the x alpha 1 as well as x alpha 6, and may also be contained in something else. So we have to choose in which region we regard it as belonging, I mean in which of the sets x alpha 8. So with these arbitrary choices, any path gives you a factorization, but you can change these choices if it belongs to two sets. Okay. Now as far as pushing across a brick is concerned, now suppose we have this path and we want to push it across 3. Okay, then what we have done is we have a factorization up to the left vertex, so we're pushing it across 3, and a factorization beyond this which is not going to be touched. Okay, meanwhile we had a factorization which was two paths, this one and this one, merge them, so you have a single path. Okay, but first regard them both as belonging to 3, R alpha 3, then you merge them, so you have a single path belonging to R alpha 3. Now a homotopy will push it to the path here, and since we are looking at homotopy classes in factorizations, this path is going to give you the same factorization. Okay, so the path has changed. In fact, it's a loop. I've been saying paths loosely, but we did the work to make sure our vertices were loops. Now this path has changed, it's going above, and now I refactorize it by breaking it up into pieces. So then I get a factorization, and I need to a factorization I'm saying because there is a choice of which region we are regarding segments as, but a factorization corresponding to these paths. Any two such factorizations are equivalent. So every time we push across a brick, we get an equivalent factorization. Now you successively push across bricks, you end up from the lowest to the highest. The lowest is equivalent to the first factorization and the highest is equivalent to the last factorization. Okay. So these were the steps. Basically we wanted to show that the kernel is in N. So we took two factorizations, we saw them having assumed they have the same image and showed their equivalent. Our goal was to show they were equivalent, and if they're equivalent, then they're equivalent as elements. Then the elements they give in the quotient by n are the same. So that will tell you that if you have two elements in the quotient by n which go to the same element in X, in the fundamental group of X, we have the same. Then they are equal to each other already in the quotient by n. And the way we showed this is that same path in n means that we have a homotopy. And when we have the homotopy, we break it up into these bricks, make sure each vertex goes to x0. So now we have loops, and once we have made sure vertices go to loops, then vertices go to edges, then these paths can be regarded as loops and in products of loops, hence giving you factorizations. And moving from above to below is pushing across a brick, which is moves, relabeling, and homotopy. Okay, with this we complete our sketch of Van Kampen's theorem. This was the last main result to prove. We'll get a few applications here, including some purely to group theory and of course topological applications.